now we know how striking you have to continue collect data to generate massive information. In a way, let's get back to this. So what I'm trying to tell you is really give you some real hand experience for a lot of people who may not have a chance to operate this high-end instrument like Titan or Glacial. So maybe this is the time you can see it. So for us doing a lot of tomography, based on what I know, most of them use a Cryo-EM developed by David Maxtranoni many years ago. This package became very powerful and flexible, as we mentioned earlier today. So that's just to give us a really nice platform for data aggregation, for particularly for tomography, but also for single particle. So as I mentioned earlier, this is the normal overall flow. You changing angle, you correct imaging shift, and then you do this fine correction. You know, that's almost like 25 years ago. So the workflow is the same. So the how to access, so the key software now we use is Cryo-EM. So I want to use this opportunity to give you a little bit more information about, there's a couple of things very critical to really make this work. And so you need to understand some kind of basic parameter. The flow is slightly can be changed, like a low dose setting. You can have a low dose setting, and defocus, and the panel could be slightly different. And this is navigate file, and then you have this camera setting, and this beam intensity setting. They all could be very overwhelming at the beginning. I would just give you, so we also mentioned earlier today, there's a different way to collect data. As you may hear from earlier micro-EDs, you have to use this continuous motion. And that was very mainstream for tomography for many years. But now I think this Wim Hagen scan seems became very important. But this is back and forth. It's not necessarily stable, take longer time. But that's presumably give us the best detail. So I will use the Chen Xu's script as an example to show you how we can use it. So, and again, this can be downloaded from his website. So before I start to show the demo, I want to tell you a little bit of my experience. I hope this is valuable. First, obviously, if you really want to decide, there's so many packages available. If you decide to learn Cryo-EM, there's a really nice website to show you how to do it. But more important, I think for me, I literally visited Brandeis many years ago, just watching Chen Xu to collect data using Cryo-EM. And that's what I'm actually hoping to provide you today, just to show how I collect data. So you at least get a sense, the practical sense, how to collect data. And but you really need to work with the expert in your facility. For example, in my case, I'm working very close with Senping Wu. She's our facility director of Cryo. So I have to working very closely because she have to do the calibration, getting the software installed. There's so many practical things behind the thing. So I obviously don't want you to go through this myself. I don't even know actually. And also after this one, you can getting a lot of help from the Cryo-EM mailing list. And if you start using it, so you want to be part of the mailing list. And obviously the last one is you just practice. Basically try to optimize setting for best possible outcome of your own experiment. So I think that's really very important. And then many people may not necessarily realize this Cryo-EM be developed for 25 years now. So it's evolving and so things changing. But here we are. Before I show the movie, I hope you can see it. Again, this is a real imaging of, I tried to pre-record it and a couple of days ago. So again, you can see the interface with the imaging in the middle. This particular imaging happened to be a low mag imaging. We have as I go back to here, this called view. and the focus, try, recall. This is what we have called view mode. In this view mode, if you use this 2 micron hole as scale bar, this 2 micron, this view provide overall what's happening in this particular area. And also, I want to also pay attention, this is a minus 106 micron defocus. So at this particular setting, so we can actually see the target interest pretty well. So that basically means you can select the target. As I mentioned earlier, you can add position, each of the coordinate based on your interest. For example, here's one. And then this coordinate will be added into this navigate panel. And presumably this will continue. Since this is a demo, so I will just show you, and this is a very long demo, 1.5 hours. So just feel free to ask questions because this is a real data acquisition. So I basically want you to know how actually data was collected, how we're going to switch into a brand new sample, and then we loading the new sample into the into the microscope. This is all remote control. So presumably someday you may have this opportunity to control this yourself. There's one thing I do want to emphasize, tomography is very much different from single particle. On this particular case is you have to be the operator to select target interest. You can ask somebody else to collect data for you, but if you don't select the right target, you could easily waste all your time and the precious time on the Titan and the other Glacio and other high-end instrument. So that's why I think this is something if you want to collect tomogram, you prefer to do it yourself with minimum help from other people to make sure this. So this is all setting can be done remotely. So again, this is I can start play. You can see this is about 80 minutes. So this happened to be the last target. We're going to collect 2 series. So the last one is called A. We're going to collect 2 series. The first one they collected, they loading this script called fast tomo. So they start to use do eccentricity, finding eccentricity. As we hear from Michael ED talk, eccentricity is very important. So the stage was tilting. By tilting the stage, make sure the specimen not moving away from your imaging area. And this is what we call -24 to +24 tilting. By tilting this one, minimize the imaging shift so you can find in this eccentricity. After you found the eccentricity, they will update Z high, and then they will do the next step, want to make sure the focus is correctly. As you can see, this is autofocus. And so what's happening is they will use adjacent area and to do focus. This will tell you the focus number from original -6 to about -3.8. And now because focus is now correctly, so they're ready to collect the 2 series. And so the fast tomo was now used. Fast tomo idea is to skip a lot of focus and step using tracking after. Basically use your recorded image as tracking target. So this is the first imaging was taken at 0 degree. At 0 degree, you can see there's a 10 nanometer gold, multiple 10 nanometer gold. There's a bacteria. And here there's another bacteria overlapping. As you can see, this overlapping area is much thicker. And then they go back to low mag. After tilted to 3 degree, they want to use a low mag to do tracking because to minimize the dose. And so now they do the tracking, they'll go to 3 degree. And instead of doing focus and the tracking, now they use the directly collect imaging because that could speed up the processing. Now so you can see it's a 3 degree, 8 degree, 6 degree, 9 degree, now 12 degrees. So they have quickly collected data one after another. In this case, you can see 12 degree and 9 degree have a big shift. So they correct the image shift. shift, continue to go to 18 degree. Now, so they continue to collect data, and as you may notice that this is collect the movie stack. So now it's 24 degree. And the way this particular setting is, so we want to collect data from 0 to 24, then go back to 0 degree. So after they finish 24 degree image, so then they will go back to 0 degree. And as you can see from here, so they go back to 0 degree and -3 degree to do tracking. And because this back and forth, the stage is unstable, so typically have a big shift, as you may notice that here. At the low mag, have such a big shift. At the high mag will be big jump. So we work with Chen Xu, develop the software to have this tiny change. So make sure at the -3 degree, you can see the imaging, the area tracking still in the middle of it. And then again, the gold remain in the center. So this is go to -12. And so every 3 degrees, so you very quickly collect data. Because whole idea to have this so-called fast formal is you can control based on your own need, and they're also able to collect data as quickly as possible and skip a lot of steps that was required typically, like focusing, tracking. And now this will go to -24 degrees. So the idea this will continue collect to 48 degree cube to continue the image. And so you can see that everything is saved. The data was saved a couple of days ago, and this will continue until they finish. And when the jump is too big, they were retaking the picture, and based on how much shift it is. And so now you can see typically it's about 6 to 7 minutes to collect this 2 series. And this is actually the last one of this particular sample. So we will, after finish this one, and then we're going to switching to a brand new specimen. So any questions so far? If you have, maybe Jack, can you, if you saw the question, maybe you can ask, because I'm not going to see the.
We don't have any questions so far.
Yeah, but feel free to ask, because this is going to be a long, boring video. So
okay, do you want me to stop?
Have a question, just ask. Yeah.
Okay,
so,
I'll ask the question.
And now they go back to finish the this is a go to this plus 27 degree, and you may notice that the defocus value is changing because we use a pre-calibrate defocus value. The defocus is pre-calibrated, and that's one reason we can skip the defocus, because they use the curve, pre-calibrate curve to collect tomograph. And so now this is go to 39, and and it's almost finished. So see, this actually tell you this is the last 2 series out of in total 86, and this is the 6 second to finish. Now it's done. So after they finish, they tell you, okay, all the 2 series is done. Okay, so you see how I operate. So first go back to see this particular grid have this very low mag montage. And this montage, you can see the target interest focus on the center. Every plus coordinate is so here we are switching to another monitor. So this is a big jump. This is the Titan computer. So we turn off the objective lens, then switch. This is auto loader. We switch it to from 11 to 12 grids. Then I call load, and this take a longer time. So there's a big jump here. So what's happening is we switch to a different monitor. This monitor is control the mic scope. Another monitor you saw previously is a control K2, K3. It's basically, and that was control Cryo-EM. And in this case, you now know we switch into a brand new specimen. And this all can be done remotely. So that's actually very important for many of you to know, because if you want to access the Brookhaven National Labs Cryo-EM or Titan, and you may have to operate remotely. And that's turned out to be a big advantage because you can actually getting a lot of things done and without the safety concern.
Hi, Dr.
Also,
Liu,
you don't
two
need
questions.
Yeah, go ahead.
Sorry, I feel bad interrupting you.
No, it's okay because this is a long break.
Okay, first question, can you use FastTomo to collect multiple data points in sequence, so set up an overnight data collection?
Oh, yeah. That's exactly what's the purpose. I will show you later.
Okay, and then next question.
Yeah.
Nice demo. Do you know what exactly are skipped in FastTomo data acquisition to speed up?
Say that again.
Do you know what exactly are skipped in FastTomo data acquisition to speed up?
Oh, there's two things to speed up. One is we don't do pre-tracking, because typically we need to do pre-tracking, and so I can answer this one, but right now I want to tell you things right here the screen. So this is basically the different mode from view focus. So we want to set up the okay, this is kind of too quick now. So, but because the Titan is very expensive, as you all know, you have to. But this is why I pre-recorded. So hopefully you can do it yourself, watching it yourself. But here is a break because you see when we change in specimen, there's about 5 minutes to every specimen changing. So that basically means this is the time you cannot do anything. You don't want to walk away because you can see there's a lot of things going on in this status. And back to what the first question Jed asked is, I think the key thing is we skipped a lot of focus step and also skip a lot of tracking step. By skipping these two, then speed out the processing. But you do need to make sure that the microscope stage is well behaved. So that basically means you need a good calibration, including focus and other calibration. So that's actually one of the main reasons speed up.
We have a follow-up question to that. Can it be realized in serial EM built-in functions without the FastTomo script?
Oh, yeah. That's actually because 10 is working very close to with David, because this is still a testing stage. But if it became more mainstream, more user friendly, I think David and Chen will probably easy to incorporate. That's actually what they did with this Wim Hagenstein. When Wim Hagenstein developed at the beginning, it's a script, but now it's a part of the Cryo-EM, newer version of Cryo-EM. So you can see now it's almost finished this loading the specimen. So from the 11 grids, now we switch to 12. And this is in total about 5 minutes. And so after this one, you will see how we able to collect montage and then collect the image, use different magnification to control Cryo-EM to select area interest. And this is a very long video, but I want to make sure you don't have to remember every detail, but if this video is available, so you can download and watch yourself. So now we finish. So we open the column. Open column. And then our microscope have to be based on what the sampling knows. So typically the Z have to be 100 micron. So we move the Z to 100 microns. So now we don't need this panel anymore. We switch back to another K2 computer. And so this is very important. This is called search. It's basically low mag. I don't know exactly how much the mag is, probably 50x. Because at 50x, you get this picture. So they are taking picture. This is old picture from previous. Now you're getting this low mag picture. You can see the grids of this, a lot of bacteria here. And then we want to take a montage because I want to see the whole grids. And I select this called scanning mode, basically very low mag mode. Then 6x6, basically take a 6x6 montage. And then I give a name. And I give a probably called low, basically low mag montage. And basically you can have a good view of the whole grids. And I try to save the data into a folder, but the words is so small I cannot see anywhere. But it just called low. The idea is you use this so-called a search mode to collect a very quick low mag picture. And then you press the start. Okay. So then start to take a montage of 6x6. This is about 6 minutes. Okay, so they are taking picture one by one, and then in total is about 6 minutes. 6 minutes. So you can see this is a bad area with broken grids, broken carbon. And this is very bad. This is very thick ice, and some broken area. This is a real sample. And again, this is a new navigate. So nothing is there, brand new. Basically, I open a brand new one from here called navigate. And this is a still old log file. You don't need to worry. But and this is actually the data, most recent session we happen to have, because you all know Titan is extremely precious. So we had to find a time to make this demo possible. And the good news is this is a real sample. So everything was done within about 80 minutes. So presumably you have to keep that in mind. If, at least in principle, it is possible you're loading a new sample, then find the area of interest, then select to collect Q series. And so now you can see this is about nine picture now. And you may notice that this is actually one of the most important steps, because you need to decide where to collect data, which is a good area. And that's why this is typically cannot be replaced by other people, because nobody knows what's looking for. If I'm not telling you what this sample is, you have no idea where to should be looking for. So that's why I think the user, whoever what your project is, if you want to do tomography, you really want to be involved. And to a point that, for example, like this is a much less concentrated area, and this is a completely broken area. And some area is dense, like this is a very dense, so presumably very thick. But in this case, you really don't know this is a good sample or this is a good sample. And because we just don't know. And but at least you get an overview of the specimen within about 5 minutes to 6 minutes. So you use this 6x6 montage to provide an overview of your grids. And as you know, how big is your montage depends on your magnification. If you use a very low mag, you can take this montage very quickly. If you use a very high mag, this montage will take forever. So it's in our setting, we are very lucky to have sampling setups. So it's very nice at this low mag. So we can literally use about 6 minutes to getting a very good view of the whole grids. And then we can use this so-called search mode. That's typically is about 2000 X in the Titan setting. So then we can getting very quickly to to getting the things we want. And one of the nice things is this, back to one of the questions I would ask is, the nice thing is to do this is make sure we can do overnight data acquisition, because two series take a lot of time. And typically the night time is the best time because the microscope seems more stable. And so I think we're almost there. So this is about 2 more minutes. And as you know now, right now nothing's there. But after they finish, the montage file will show up here. And since we are here for waiting for 2 more minutes, there's a couple of things you may still want to keep an eye. There's a defocus. And this is a tilt angle. And there's a many control of the microscope. So pretty much you can control the whole microscope operation from this monitor. Occasionally, you may need to use another Tech9 computer to do some like auto loading, specimen switching, and other thing. And so you can just use this one and remote control. And it seems very effective. So I think we have 1 more minute. Oh, here it is, Mac. It's 175x. So it's very low Mac, 175. And that's the reason we can getting a very quick overview within about 5 minutes. So this is Mac. So we have a multiple Mac. One is this 170. In the view, it's about 2000. And this record and focus is really depends on your interest. For example, if you want to get a very high resolution, you use a very high Mac. In this case, the record is 64K. So it's very high Mac. It's almost like single particle data acquisition. Okay, so we are almost there. And so this is why you need a patient and hopefully you don't waste much time. You know, I always told the people in my lab, when you're using microscope, it's in the war zone because microscope is so expensive. And so the more you can get out of it, the better. Okay, so there's one obviously things will show up very quickly. So this, the different Mac, you want to be sure they're in the same area. So they have to be aligned. And so I think it's there. Here it is. Then they ask you for yes. Then we enter with a new object here, brand new object. And you can double click here. Then you can zoom in. This is what I call the kind of like my Google map. So you can zoom in to different region by changing the middle button. You can zoom in, you can moving around. So you can see the concentration of the sample is very different. And you don't know, as a new sample, you really don't know which is better sample. So the idea is you select, do a very simple alignment. And for example, I see this object. So I get add object, so called add marker. So the number 2 is this area. Okay, then we want to go there. We go to this place. And this is what I call hole, basic empty area. So I put a name called hole. And this one you can give a name called marker or whatever. Okay, so then you want to go there, go to X. So the stage will move to this location. Okay, stage will move there. And after finish, you set a view. View as a view is different Mac. Look at the view, we are switching. And just like Tamir mentioned earlier, when you're switching from different Mac, we'll have a delay. So there's a delay. And now you see it at the 2000X. And anyways, you see this area is the same as what we label. So we won't do this called reline to the mark. So basically align these two objects to map. So it's about a couple micron off. So now what we see in the two will be the same as what we see here. The two will be the same. So because we now did alignment, so now we can start to select, to look around, so which is the area target. And in this particular grades, some area is very, very dry. For example, like this area. So this is one area. We call test, just want to see what's this sample looks like. So then I go here, go to XY. So we'll go to this, this location called number 4 coordinate. And this is a very important step because you need to figure out which is the area of what's to collect the data, right? So the one thing is have to be vitreous. And this is, for people don't necessarily know this, and this is not a very good area because you can see the ice looks very good, very dry. So the bacteria in this case is not frozen, it's not embedded in the nice ice. So you can see the background looks kind of dry. And there's not called crystal clean, in my view. And you also can see a lot of dot. The dot is happen to be the gold marker, about 10 nanometer gold marker. So anyway, by look at this one, so our idea is this is really experience you have to figure out. I think this is not good, too dry. Basically, ice is too thin. They'll not be embedded in the, then I choose a rather thick area, and this looks thicker area. So I add a point, then add a point. So you can see I select the area around this neighborhood. And obviously this is a broken one. You don't select this area. Okay, so this is basically, as I mentioned earlier, we try to use a relative quickly to getting things done, but you don't want to waste the time here. So we hope to collect useful data. So in any way, we very quickly select area that interest. Then I want to check it. So I go to the number 4, 5, and then they move there. So 2000x about. And now if you compare this with previous one, this is much beautiful because the ice looks very clean with some gold mark there, but it's very even. You can see it's very even. And obviously this is experience. So I think the good news is that you can always take a picture yourself, then decide which is good. And so this is what we see in the vitreous ice, has to be thin, has to be clean. And then this is a nice area to collect data. So I said, okay, I want to collect data now. Put the A there. This is called acquire, is A. This is very much similar like a single particle. So you just collect the area A, okay? And I'm going to collect about a 5 montage. Now I need to define the montage. So I want to use a view and collect 5 by 3 montage because I roughly know the size of the hole and I roughly know the mag of the view. So then we give a name called intermediate, I think, or called medium. So this is probably the most important montage you want to make because this is the montage you want to have a good image contrast. So one of the person asked me early today how to select the area. So this is why you need to make sure this view have a very good contrast. And so you know where to collect the data. Basically, this view had to be good enough to help you to define which hole, which exact location you want to collect data. And so I give a name. So, okay, so now I want to collect data now. So I want to do this so-called eccentricity. Then I collect montage. Everything else will be removed. So what's happening is now they are ready to collect data. Serial EM is collect the data now. The first thing is they call finding eccentricity from the first target, called number 5. So they move there, then they tilting the stage. Okay, they tilting the stage. So I want you to see this one, see this portion. So I'm changing this a little bit. Okay, so this is now they're doing finding eccentricity by tilting the stage and minimize the stage shift, imaging shift. Then you should be able to finding the Z high, eccentricity Z high. And then the imaging, even though it's a zoom, I know it's very hard for you to see the imaging clearly, but at the minus 100 micron, and the exposure time about 2 seconds, and you can very much see, like this is a bacterial cell tip, and you can see many feature and things that you know, if you're interested in this bacteria, you should be able to see a lot of feature that can help you to decide this is the area you want to collect data. So now this is basically going on now. So I can zoom in, zoom out to see, and this is the whole view because this is K3. The size is elongated on y-axis, and you can see this is the ice because this particular grid was loading multiple times into Titan. And then that's actually pretty common now because if you want to send in your sample to a national facility, so you probably want to screening first, make sure you're not sending a junk there. So, but unfortunately, you always will introduce some kind of ice during this transfer. But good news is they are not everywhere. So you're still able to find in a lot of area interest. So this could be a longer time. And this, as I told you, this is 15 image. It's about 3 minutes per this montage. And you will see after they finish this one, you are getting the first montage. And so one of the nice thing about this is by working closely with Senping in my case, so I can figure out, found a problem, then she will help me to fix the problem. So this is the place you want to know whether there's a problem. So when you stitch together 5 by 3 picture together, you want to make sure they stitch together properly. If they are not stitched properly, thing like this one, you can see they put together very nicely. See, you can see 5 to 3 put together, and this is a grid bar, and you get a nice overview. And then this software will automatically go to the next one to do this. So this could keep going for another 5 minutes to 10 minutes. So any questions so far? And they also doing this finding eccentricity because each location, the height is slightly different. So each location, I asked the software to use finding rough eccentricity. So they will basically do the same thing, tilting the stage, and then take montage. So now you got it, the first one finished. There's 4 more to go. So it's about 12 minutes.
We have no questions so far.
Oh, thank you, Jack. So, and after this one, I get a tie with it. I said I should stop it. So I put an end a cryo. So after they finish this one, this will stop. And because we want to show you the next step, hopefully quickly, because the nice thing about this software is it become very flexible. So you can go to here to acquire, end the cryo. So after this one, we are finished. And also you can see this is the time. this will take another 12 minutes to finish all the sign project. And I don't want to wait for 12 minutes. So I said, okay, why not stop it? So I asked, end it. So I want to start to collect data. We'll put it this way. I want to make sure the sample is good for collect data before we spend too much time collect other area. So I want to do the next step quickly, then come back to fill the gap. Okay, so it's almost there. So after finish 5x3 montage, and then the project will stop, and then there are some message came out very soon. Okay, so you see now they finished second one, because I put a button there, so they basically finish. So what obviously next question is I remember I forget to put an aperture in, so I should put a aperture back. This is the objective aperture, and this is actually very important because as you all know, tomography is a very poor contrast. So to have an aperture in really help to contrast. But when you have an aperture in, then you cannot get in low mag image. So that's why I stop it. Then try again. So in this case, say check it. Okay. So now I'm collecting data with aperture, objective aperture in. And without objective aperture, I think it will not make a big difference at this particular setting. But if you want to collect data at high mag, the with objective aperture in will help the contrast. So this particular case is the only difference between this area is I have objective aperture in now. So we have a 2 area was collected. And while I continue more, because as one of the early questions, I remember correctly, if you want to collect this data overnight, so you want to make sure you have enough target of interest, and so this do take time to select an area because it's not every hole have a bacteria of interest, so you have to find in the area typically. And in our case, we in a good setting, good sample. So you need like 5 to 10 this type of montage to find enough target to go overnight. And in this case, if you can do a simple math, if it will take 7 minutes to collect 2 series, so in 1 hour, you can collect about 8 2 series. So overnight, it's at least 122 series. So basically means you need to find 120 targets. And you don't, and then obviously for other sample, this may be piece of cake. And this is slightly difficult because our interest only on certain region of the cell, not everywhere. And the cell is very long, elongated. So I will show you how, but it doesn't matter how you select it. Typically, it takes a little bit of time to find in the, and again, this is all ice contamination. You can see this droplet for the ice and 2 micron hole. So this basically means that this ice as small as 0.5 micron to like 1 micron. So I think this is pretty much is for the. I don't think if I remember correctly, I don't think I finished all of them because time. So. Okay, so I think this will continue for another 5 minutes. So any other questions so far?
There's one question we just got. I missed if you're using an energy filter for data collection.
Oh, yeah. We have an energy filter in. And I don't think we have a cameras here. The energy filter is in. And actually, this is a very good question because as you already know, we have 3 different settings. One is called search. The search is about 175x. And then we have a view is 2250. So because they are different MAC, so the slip of the energy filter is different. So we use a much bigger slip for low MAC. For high MAC, we use 20 EV slip. So we do use energy filter. Because we use the energy filter, so we have to do this zero loss peak. And this is actually important. I think during this demo, I think I did that one. You will see, I at some point I did this energy filter zero loss peak. So make sure that the slit for energy filter have to be in the center.
Okay, thank you. That's the only question we have right now. I'll let you know if we get more.
Oh, thank you. And you can take a coffee break now. So there's 2 more minutes. So you can see here it is 4:20, 4:30.
Okay, sounds good. Thank you. So this is gonna be another 2 minutes waiting.
Yeah, I think it's actually 4 minutes. Sorry, 4:20. You see can you see this? Because can you see this value?
It's a little difficult.
Okay.
But okay.
There's a time here. They are basically estimate how long will take to finish the thing.
Oh, okay, I see. So 3:45. Okay.
Yeah.
All right, sounds good.
Okay, so this is the last one. So we'll be finished in 2 minutes. And you know, for many user who is actually new to do this is a very important step, because when you look at this one, you probably already know do you see anything of interest. If you found you're not seeing anything after you collecting 4 or 5 picture like this, the chance you're going to see anything is low. So this is actually a very important step. You want to make sure that you optimize the parameter of imaging condition. So you are actually see something rather than you wait for the last minute. So if I were you, actually pay attention on this imaging. And if you, in the real time, you can actually zoom in, zoom out. This particular settings, you see whole thing. But we can zoom in, zoom out to just see whether this image looks right or not. You know, this is why it's very critical, because the Titan and the glacial time is very, very precious. So if you see this is bad area, the imaging done looks good, we stop right away. That's why there's a function called stop. You can actually stop here. And so all this button just make sure you utilize the resource properly or more effectively. So anyway, I think but the good news is that the whole time we are using for this data acquisition is roughly about 15 minutes. So it's not way too long. So it's perfect time for some coffee break. Then you come back to make sure you select the area for the data acquisition. Okay, so we're done. Okay, so this is finished. So you can click each of them. Then you can zoom in. Again, this is almost like a Google map. You can look at them, and clearly they are different. Some is slightly more dry, some is less dry. And this is zoom in, so you can moving around. And before I do more, I use this ice for alignment purpose. What's basically mean is I want to make sure when I collect data, I select this area will be collected a high mag in the center of my high mag image. So this is a very important step because you may collect a lot of data, they all wrong area. So how do I know it's right? So if I go to preview is almost like record mode, except much lower dose. And so I go to 64K. And so you can see my center of the gold is not in center. Okay, so I center it, then I reset image shift, retake again. So my area is on the top of the ice, right? So, okay, now this is a very critical step. So I want to go to view. And my hope is view, the center of the view and the center of this record are identical. So you want to check it. And if the microscope and everything is operate in the good shape, so you will do minimum thing. Like this case, they are very, very good. But I still want to be sure they are precise. So I move this down a little bit. Then I call, it's called setting, set. So now both record and the view are aligned. They are basically identical area. They are basically in the same area. Okay, so now I want to go to whole. I think this is whole. I want to go to whole to check the dose. And to make sure we use the optimum dose. So now, because it's empty area, nothing's there. I take a reap. So I switch to Gatan GM, take a picture, as you see, nothing. However, there's value. It's in this, because you may not see very well, it's called 7.3 electron per square angstrom. And then I can do this zero loss GIF tuning, not tuning, zero loss peak to make sure this is in the center, and zero loss offset previously was done multiple times. And now I did this one more time to be sure I know the energy is in the filter is in the center. It's basically a line. And each step have to be done precisely. This is very good, so it's 0. So then I can switch to this one. So I go to setting. So based on the dose, when I collect data, we typically go to very low exposure time because to minimize the damage. The record is I want to use the time based on the calculation. And then I save my data into a folder that is matching with other. So now we have a record time for each image. Then use dose fractionation, dose fraction mode. And then everything else, it's, you know, they are there, you can see later. Then try very short exposure time, record everything is very short. Okay, so this basically means we are using roughly about 60 electron dose in total to collect this Q series. So again, I want to show you one more thing is where is the focus area? Focus area is off, I think. Okay. So here's the focus. You may see the focus is here. So this is going to be my record mode center, and the focus area is off, about 2 micron off. So I use this for tracking purpose for focus, and this is going to be my area of collect data. So everything looks good. Now I'm going to find my target. Clearly, this is really depends on your own interest. For some people interested in this certain region, for some other people interested in different regions. So you want to add a point, and you just find the area, whatever you're interested in. In this case, we are interested on the cell tip. So I select it, then select another area. So you just basically quickly select everything. As I already mentioned numerous times, this is a war zone. So you really want to do fast. You don't want to just wandering around, take a break. So you want to minimize the time you can get in as much quickly as done, you know. And so you want to find your, so for people who can optimize your own sample, this is the basic step. You can make sure you have a better sample. If you prepare the sample yourself, you can say, okay, maybe I can increase concentration of increase this and that, you know, or maybe lower concentration or higher concentration. Because ultimately you don't want to spend just hunting for your specimen of interest. And so the better sample you have, then it will be better. So as I already said, the clock is on. So basically, as the moment you start to use Titan, the time is on. So you really don't want to waste it. And in our case, 9 o'clock a.m., we have to switch to another user. So if you cannot getting anything done within the time, the next user will start it. So your sample will maybe wasted. So clearly very important. So the nice thing about Cryo-EM, they incorporate a lot of nice cool function. So the more you feel comfortable with it. So I quickly select some area, and then within few minutes time frame, so then I will able to collect data. Basically start data acquisition. So you can add, right now, I think we add about 15 now, target. And so and obviously, if you want to collect 120 target, you can easily spend a lot of time, precious microscope time. So we typically start to keep the microscope running, then use another dummy version of the Cryo-EM to do what we are doing now, because you don't want to waste the microscope time. So, but this is a kind of a more realistic circumstance. So we're done. Okay, now I want to do the very critical step. So we want to start collect data. So we can collapse. Then you just need to click A. Basically, just like a single particle, every area you selected will collect image. So you save your navigate file. And okay. So here's the place we want to change this so-called tomo, fast tomo. Okay, so you need to define where you want to collect data, what's the tilde range. So in this case, we choose those symmetric. And we also want to give a name. So make sure the name is there. So this is called open file. We also have a close file. So that's basically part of this fast tomo script. And so with this in mind, now you're basically ready to collect data, right? So you see every place is already A. And to collect data is exact same as before. Is now we skip this. We use this open file. So you have a file name. Okay, then you want to run this fast tomo. Then you want to close the file. So that's all. So we can get the data. This is basically the exact the starting point when we start this video. At the beginning, so they are now basically start to run this project in the script. So what's basically the script will ask to do is a couple of things. So this is the start fast tomo, and then they call reline to item. Basically, make sure you find in the item that you selected for collect data. Clearly, I'm not select this area because this is on the carbon. I'm select this area, so they found in this area by doing the cross correlation with previous recorded image. And then they do this eccentricity, finding eccentricity. So by tilting the stage from -24 to +24, and make sure the eccentricity is good. And then they adjust the Z height, to minimize the tilting cause the shift. Okay, so they found the eccentricity. Now they want to do the focus. They want to do the focus. Okay, autofocus. So then they use a JSON area to do focus. They measure the focus. So then we set the focus to 0.4 micron. And then do the use exist focus calibration. So what that basically means is they are now ready to collect data. That's exactly what we started at the beginning. And so basically I just try to show you, we can use stuff from a brand new grids, then take a low mag montage to have then this is basically the first image was taken. And this is gold fiducial marker. This is the bacteria, the cell tip. And this 0 degree then start to tilt to 3 degree. And to do 3 degree, use a low map for tracking to minimize the dose tracking, and then collect data. Okay, this is 3 degree. Then from now on, they became very fast because now they collect 6 degree, 9 degree, and 12 degree. And because switching from different mat take a lot of time to normalize to the lens to normalize. But once they start collect data, it became very fast. Okay, so this is basically connect to the beginning. So it's basically do the same thing. It's very boring. So as you already noticed that. And but key thing is, this type of thing is not that useful until one day you want to collect data yourself. And then you realize maybe devil is in the detail. And that's why I mentioned earlier, you really want to, if you are facility manager, and then obviously this is the pain you have to go through yourself. But if you are a user, you really want to make sure you work closely with the facility manager to make sure, you're not struggle by yourself. And there's a lot of detail there. And so things just basically keep going. We'll collect a lot of data. So in total, we have 20 minutes to go for this tutorial. But we are very close to, there's one critical step I want to show you, hopefully very soon. This is probably part of the tutorial very soon. So any questions so far?
Looks like there's none.
Oh, that's good.
Yeah, you're doing a good job. I think
yeah.
I'll
So
stop you if
easy.
there's any questions.
Yeah, it's very easy. Yeah. And I think if you happen to use Cryo-EM before, this is just like simple. But if you never did before, most of the stuff I'm doing doesn't really mean anything to you. And but later on, in case you're going to use it, maybe this video is still available, so you can look at them. Maybe very hopefully well, and this gives you a sense of the workflow. And so, I typically, if I use and collect data myself, I will look at them, and this for the first data set. See whether they tracking properly, see whether the focus properly, and all this thing is easy to fix. The good news is to watching them for like 8 minutes, it's not going to be killing you. But if you notice problem, you can fix right away, hopefully, and hopefully fix the right way. Yeah, and I think obviously all the parameters can be changed, so you can change based on your interest. I would suggest you can start with this parameter, whatever the parameter it is, and then tuning them slowly based on your own sample or own interest. So one of the main things you may already notice are typically the image looks very nice, and then getting worse and worse because when you go to high tilt, and the spacement became very thick. The second one is because those radiation damage, the contrast became very poor. So it's very natural, So and that's you're getting worse image, and but in any case, I think we are so far so good. So I now they switch to the next area. So this tell you how much time for this particular data collected, and also give you an estimate how long this project will finish. In this case, it's about 2 hours, and this job will run 2 hours. But as we discussed before, the goal is hopefully set up a job can run overnight, right? So and also try to getting as much data as possible. So in any case, I think this will continue. So I will most likely switch to a dummy version very quickly. I think this is one of the nice feature of the Cryo-EM. And so see, this is now they moving to a next target. They can find the target, and then they clearly do the next couple of steps, including eccentricity, finding eccentricity, refine eccentricity, and the focus. And you know, all this step is critical. They are not, they go through all of them. I think I will show that demo. And let's see this, how long could it? This could take forever. So let me see. I think I don't recall. So this basically just is watching a very simple, and the focus again, and then everything else will be this similar. Let me speed up a little bit. Ah, here it is. Okay, so what's happening is when they are collecting data, it's boring, you know, and you can do another thing we call dummy. So what you can see is now we go to this called dummy. Basically, dummy is you can basically parallel operate. So you found that same navigate file. I make a copy, paste it. So we have a so-called paste option. So you can see everything we see previously is there. And then we can add more target. We can go and select more. At the meantime, you may notice that the background still collect data. So we are basically not using precious microscope time to just finding the target. And instead we are doing parallel. So then you can take a break, do whatever you want, you know, enjoy the processing, try to be more picky than you could be, and try to find the best looking cell. And you know, because you're not wasting microscope time, so everything still operate in the background. And so you just add more sample, and also based on the feedback you got from previous 2 data set, now you can make adjustment, including, you know, how to select better area. And if your data collected previously is not good, then you need to change your criteria. Which is the better area? Which sample should collect it? Do you have enough goal? And you know, all this just teeny bitty tiny detail became important, you know. And I think this is a very cool feature. I actually learned this with 10 many, because if you imagine for single particle people, you do the same thing. You cannot afford to select 1,000 target slowly by using microscopes time. You can easily getting started, getting your data acquisition started, then take time to select area. For single particle, it's thousands of target. For tomography, it's like 100 target, but still equally take a lot of time, because you can see this is very selective. You have to find in a area that may not be everywhere. Could take a while.
We have a question.
Yeah.
I might have missed it. Do you need to do auto-eccentric for each grid square you select before you import the navigator file to serial EM dummy?
No, you don't need a, because everything is already updated. See there? This is your centricity height is already updated, because when you click the montage, you already automatically update the. We are only look at this montage file. So each montage file have a defined Z height. So they already incorporate this centricity in. So now I think here's a critical one. I save it. I close my dummy. Then I said, okay, I need to stop this one. Stop this current job running on the microscope. Then end a cryo. So in this case, they will finish this area and then stop, because I asked the program to stop. And then I can incorporate the new data I use dummy to create. I can merge the data back to this file. So then I can run overnight. So it's pretty effective.
Thank you. Next question says, thank you for a nice demo. Please advise, is it really needed to optimize the ratio of gold particles to sample while making sample?
Oh yeah, and but typically the gold that you got from the same source, so you roughly know the concentration already. So you do need to play around for any new gold solution you got. I would suggest you getting more. Gold is not that expensive. For this case, you can have more, and but later on you want to reduce it. And so you do need to play around a little bit. And it also depends, sometimes it depends on sample. Okay, see, now I finished. So then I merge. So this is my current file. So I have about 20 target, roughly. Then I going to merge file. This step is kind of quick. So then I increase more. Then I just add more. So now I basically have a more target for collect data. So I literally use less than 1 minute time to interrupt the 2 series. And I also changed I want to do calibration for each area, because I found that this is not skipped. Calibration is not good, so I add back calibration. So you will see what that means. I will show you. And this is all means flexible. Being flexible sometimes is good because you have all the control, but too many control is also pain. so you want to find a balance and hopefully become flexible enough, but also powerful enough to allow you to getting the data you need for your own experiment. And I think I already kind of tell you a couple of key messages. One is you really need to be involved to select your target. And also you need to get their feedback quickly. So you know what you selected, it is good target. Sometimes it's try and error. And including one of the previous question, the gold concentration is the same. The gold is not evenly spread. Sometimes some area have more gold than another. So eventually you want to find a balance that not too many, just like decorate with gold, or not just like 1 or 2, that seems not optimal for data analysis. And so I think that in all, you need to take the advantage that you can get a feedback very quickly now, and use that feedback to help you to select better target, basically. You know, I would kind of like unrelated. It's kind of like you go to a junkyard. This is a junkyard. EM grids with so many different target. You get lost, then you need to be selective. Find the best things you can find. You know, even the worst sample, you may find some best result if you pay attention. So now this is basically going well. So they stop. Now we have 26 target now. So presumably you can easily apply this to multiple of them and without slow down your microscope because the microscope continue to collect data. So I think this is good. Okay, here it is what I forget. So when you this one basically doing focus calibration. So in other words, they use a minus 40, minus 20, 0, plus 20, 40 to do method. When you tilt it, you found your defocus, and this 5 tilt angle have a different defocus. So that's one reason that we have to do focus, autofocus. But if you do more autofocus, the whole data acquisition step speed just slow down. By doing this so-called pre-calibration, so you basically use the curve to help you collect data and to adjust focus. And that's actually one trick for this script to be faster. But not always work, but anyway, that's current status. And so now we're able to continue collect data now. See, this is a beautiful cell. You can see the gold concentration, cell shape, bilayer. I think it's nice. So you want to get in this kind of nice image to help you to be sure you're on the right track. And you can find the target. You can collect data at the right defocus, right dose. Eye thickness have to be thin. So you see, we on purpose choose very skinny cell rather than this junk area. And the same data as that same sample, you could collect a lot of junk if you're not optimized the parameter. I think we can skip quickly because time is run out. I'm feel sorry you guys still stay with me. So let me just go. So this, okay. So I think that's pretty much it. Any questions? So I think it's more just matter of time. So you can see it's the same old thing, same old thing. And so question. If you, and let me finish.
Yeah, thank you. That was a great demo.
Okay, let me see. Okay, so we only finished one half of our stuff, but I will show quickly other thing very quickly. But this is a part on data acquisition because I almost certain not every of you have the opportunity to use Titan. I belong to a lucky one because I can remote control the Titan and from remotely, and I show this is possible. So you just need getting a sense, because when you really start doing yourself, you definitely need somebody's help because nobody will give you the opportunity to mess around this $8 million or $6 million microscope. But at least you get a sense how things going. So I will share my screen for a very quick update on other things, if you guys don't mind. And so, okay, here it is. So clearly there's can you see my website? So this is a Cryo-EM website. So I would think Cryo-EM and IMOD is probably where the best document software. So if you really want to learn, there's tons of things you can learn. Okay, but today I don't want to go through this anymore, but I think I will show you, if I get the data, what should we do? So this is just can you see my desktop, right? I just want to be sure.
Yeah, we can see it. Okay,
so here's the data we collected this weekend. And basically the same section. So I start with this. This is original data. If you look at this one, the one of the software called Header is one of the software from IMOD. This is the data was collected after drift correction. So this tell you this is K3, 33 image. Each pixel size is 1.38 angstrom. And the collected data was basically the same time that we was do the demo. And so this is the original data is very big. So we typically use binning, just like you can use this called Bingvol. It's also a software from iMod. Then you want the binning like 6 times. So this data will be binning to bin 6. Why I use bin 6? Because now we're all working remotely. So you really don't want to open a big file. So you work on a bin file. So now this is the file. Can you see it?
Yeah, we can see.
Okay, so this is a basic tissue. You can see they jumping around like a crazy. So, and they are not aligned, right? So what you want to do is you want to use this eTormo software to do this alignment. eTormo is, I mentioned earlier, is a very nice document. It's so you want to create a folder, then move this data to that folder. I can make this bigger so you can hope you can see better. Okay, can you see better now? Okay.
Yeah, perfect.
So now you go to folder. So the iMod, if you type iMod, it's iMod. But to do this manually, it's called eTormo. It's basically one they call Java interface. So you have this one. Open, now you see the, oh, you want to build a tomogram. And so where's the tomogram? You found it. So we want to collect single tooth access. So we scan the header. This tell you whatever the pixel size, the 10 nanometer goal. And then you just said, okay, I want to cut tooth. So you want to do pre-processing. They're all just very standard. You can pre-process them and follow this one. And you know, because this data already being analyzed, so you don't need to fix all this. I just try to use 5 to 10 minutes to finish the alignment. So you, at least you can see how the workflow. And they're all available online. So I think because the information online, just so many information, so you get distracted. So that's why I'm trying to combine everything together. So then the first thing you do cross correlation. You know, what's that mean? So you can put your mouse here. They tell you finding the alignment transformation between successive imaging by cross correlation. And when you finish, you do generate a line file. As you remember, the original image is moving around like a crazy. And because we're using a strategy called tracking after, basically without pre-tracking. That saves time, but also the generate data is not ideal. And now we can see this is basic thing, but because they already do cross correlation alignment, you can see they are much better than previous one I show you, right? So that's good, and but still not perfect. You can see them jumping around. I expect the room don't see the jumping well, but it's not perfect. Put this way, and then the next step you said, okay, I want to put a goal. Put a goal manually. So again, you put it here. So there's auto center. So the nice thing is you put a middle mouse, click here. So they will put a goal marker around it. Then you press N, the next one. Next one. Okay. So you have a multiple beat distributed around the around your target. Then you say save, and you're not going to do all of them because this takes forever, right? So what you want to do is save it. I save it, save. Then you're going to track it, track the beat. All the default is well designed, so you just track the beat. And take minimum time. Now you said, okay, I want to fix the bit. I want to make sure they are fixed. So I want to put this one here. So, okay, here it is. So I want to auto center. So here it is. when you're moving, see, they already traced the bead for you, right? So almost perfect, right? So then you said, do you find any problem, gap? And they said, oh, they found a gap because in this case, you go page up and down. You see this particular bead is not tracking. So you put a middle button, then those next. So they didn't tracking all the beats because computer is not as smart as a human being. So you can see there some beats they are not tracking properly. Okay. And so that's why even automation can fix most of them for you, but still not as good as eye. So our eye is actually best. So they said no more gap. So basically all the beat was tracking. Okay, then now you look at the next one. Do this computer alignment. So this will tell you something very important. It's the residue. How much global mean residue between the computer calculate to coordinate with what you have in the screen. And so you just want to go to next big residue. You can see that the bead is not precise in the middle of the goal. So you want to move to the middle. And this is the same, not in the middle. So you can change it. So this all can be done by, cannot be replaced by computer because you have to make very intelligent decision. And in this case, you know, it's perfect. Okay. So, and with all multiple run like this, you're happy with the bead, the green bead with your gold marker, and then you go to the next step. So generate fully aligned Q series. So this one, I think basically give you the best aligned tomogram by human. The unfortunate part is this take time. Even as little as 5 minutes to 10 minutes still take time. And but this is for certain data, this is the best one. And so now let's look at this. Okay, so now you have a Q series. If you follow this bead, they very nicely smooth. So that's what we call the nice aligned Q series. And there's multiple steps to generate homogram. So we are not use it just because for different purpose. I will show you how to do it. So it's done. We did a finish alignment. Okay, so we need to generate reconstruction. Okay, how to generate reconstruction is, so here's being, so we can use binning to show the binning version. Okay. So now we go back. So we have this binning version. This was pretty much good aligned. So, right. So that was very nice. And so we can generate reconstruction. So one of the things we use is run this script, very simple script. It's basically just looking for this align file, then use Tomo 3D, one of the package to do generate 3D reconstruction. So I just run this, so generate map. And it's, again, it's very simple script and use Tomo 3D and Qt file and the Bean 6 file to generate reconstruction. And it should be done in a second. Okay, so now we generated reconstruction. Here it is. Here's the tomogram. And I don't think you care about the other detail, but I do want to see the membrane bilayer. You can see very beautifully membrane bilayer. And this is Lyme disease spirochete. So you can see the surface have a lipid protein coated and with lipid protein. And then you can use this slicer and basically can change in the different orientation. You can change different orientation or maybe change to Z. And then presumably you can get some nice snapshot, including you can see the flagella and many other features, lipid, out-membrane vesicle, membrane, and you can zoom in, zoom out, you know. So basically we generate reconstruction and we generate alignment, and also we can have data for segmentation tomorrow, right? So the last thing is before we move to the next question. So I do tell you, so we start with this so-called Q series generated by the microscope, okay? And so I gave you a different name, it's called test, okay? So there's a lot of data here. So I go to test. Test. So in this test folder, there's just one file. Okay, so what I did before is I use the eTormo, manually go through this one. But I mentioned earlier in the iMod have this automated version. So you just need to run a script. The script is very simple. So we just run it. So I think I will show you quickly. But the script by itself is very simple. Let me show you quickly. So what's this? It's basically looking for ST file. Then you run this called patch file. If I show this patch file is from the iMod website. They basically tell you gold size, the voltage, all the parameters is from the iMod website. You just download it, make a minor change, then run it. So this is what I'm going to do. So run it. So, and the nice thing is this can run one after another. So it doesn't matter how many ST file, you can run this, and typically it's about 5 minutes. Can automatically looking for the beads. They actually tell you first do the CTF, remove the background X-ray background, just like I did manually. Then we'll do cross correlation. Then they were looking for bead, and then they tracking the bead for you, and do the alignment. They're not necessarily perfectly in some case, but majority of the case seems pretty robust. And then you save a lot of time. And by combination of manually aligned data, just like I did, plus this automation, and all together basically give you a chance to generate reconstruction, hopefully within a 1 or 2 days. And see, now they do is getting statistic, so it's a few minutes. So I just keep it running. And any questions so far, because this may take 2 minutes to finish. I know it's kind of late now. Time fly.
Give everyone a minute, but okay, we have a question. Can you recommend an iMod tutorial?
iMod tutorial? Oh, it's eTormo is the first one. eTormo is the website. I think I have it somewhere. Basically there's a YouTube version and all this. If you have a 2 series, assume you already have it, and just follow that eTormo. And the iMod have this version called Java version, kind of with nice interface. but really the power of the software is there are so many different programs there. And you know, I think that's really the power, but I don't think you can learn all of them. It would take forever. So what I would suggest you start with this called eTOMO, just what I did. And I think if I can, I think it's here. This is IMO. Then there's called tutorial. Here it is. Oh, no, not here. I think it's called eTOMO. Oh, here it is. Yeah, eTOMO. Say, you follow this. This is what I did pretty much, but they are doing more detail. Oh, sorry, not this one. eTOMO. I think there's an eTOMO version somewhere. Anyway, I think it should be somewhere. But eTOMO is the one I suggest to generate a reconstruction. And they also have a lot of nice things. I would suggest you start with eTOMO. Here it is, TOMO, a tutorial. Too complicated. Anyway, I think it's use this eTOMO with this data set. I have it before, but I don't know what's happened. Okay, so we still have a few. Okay, it's almost there. So it's
two more
almost.
questions.
What's that?
We have 2 more questions.
Okay, go ahead.
For the auto run, how do you fill in the gap of the beads which you manually corrected?
Oh, that's a good question. So, but typically it's here. You look at here, and they tell you there's a missing gap. And if the total residue is very low, you just ignore it, right? But if this residue is very high, you may have to redo it manually. You cannot, or you control the parameter, play around the parameter a little bit, just see whether you can have a, say, since we just finished this one, we look at this first. So we have a test. Then we make a bin version, basically binning them to just for you to look at them easy. See, this is automatically done. So if you look at this one, you know, I don't see any problem. I'm happy and happy with the result. I also happy with the residue that show here, very low residue. I'm happy with it. So, but if you see a jump, and then you may have to redo it manually. And that's the practice we have. And I think it's good. See, it's finished and pretty good. We basically doing this for 5 years now. The iMod continue update seems more and more robust. And so that's what I think. So I stop sharing. And any other question?
Yeah, we have another one. Have you compared results between iMod reconstruction and Protomo reconstruction?
Oh yeah, we did it, but I think to be honest with you, iMod still the best, at least based on my limited experience. Part of the reason is I think the tomography is just very difficult to align. And there's so many different things there. So I think if you can, including lamella sample, you may hear from Jianfeng, even for lamella sample, some people still try to have some gold there, just because it's make the reconstruction seems better. And Protomo is great. I use a lot. And then there's this new package from UCSF called RTOMO, very, very powerful. But even in their tutorial, they said their result is getting close to the iMod, not necessarily replace KiMod. So.
When you do alignment, you are doing underbinning stacks or non-bin stacks?
We use a unbin stack. Because this is a good question, because in the old day we use binning, but binning is not good. It's good for visually tracking, but now we use unbin data for tracking.
Is there any more questions?
That's good. So I hope you at least getting a little bit of feeling about how to control the microscope, because I did have a chance to use Li Guo's this Brookhaven's facility remotely. I learned a lot, because I found you just cannot effectively go anywhere to collect data, but you can always remotely log into somebody's computer and then control their microscope. And everything you saw today is basically I use the exact same workflow with help from Li Guo and Guobin, so I can actually collect data at presumably any national facility if they allow. so it's not bad, and especially for tomography, as I emphasized, you really have to be engaged. You just cannot hire somebody to collect data for you, because it's very selected. So you have to select interest and feedback quickly to respond. If your data is just not good, you have to respond quickly. As you already know, tomography is the future, but the future is very expensive. You have to invest a lot of time. And the speed of tomography is still way too slow. The resolution of tomography is also very slow. So basically, the only way you can really gain out of it something is effectively use the resource whenever it's possible. The software is clearly something you can control, and hopefully you can get more out of it. But if you do have any question, feel free to send me email, or maybe Li Guo or Guobin, so we will try to help you out.
Yeah, it was a very good demo. Thank you.
Okay, thank you. Have a good night.
Have a good night. Thanks for joining. Okay, thank you everybody for being here for this course. Tomorrow's our last day. We start again at 10 a.m. Our first speaker is Raphael Park from Yale, talking about tomographic data segmentation, or giving a demo and tutorial on tomographic data segmentation. And then at 11, we have Muyan Chen from Baylor College of Medicine, giving a tutorial and demonstration in EMAN2 for subtomography averaging. So thank you, everybody.